Hello everyone, my name is Hwang Ye-chan. The paper I will present is Generalized Intersection over Union, a Metric and a Loss for Bounding Box Regression, which is accepted in CVPR 2019. First, I guess most of you already know what IOU is, so I will briefly explain about it. Intersection over union, IOU, is the most popular evaluation metric used in the object detection benchmarks. IOU compares similarity between two arbitrary shapes A and B as follows. Although it is very simple and intuitive, there are many appealing features which make IOU popular for evaluating many computer vision tasks. One of the biggest strengths is that IOU is invariant to the scale of the boxes. This means that the similarity between two arbitrary shapes A and B is independent from the scale. Due to this appealing property, all performance measures used to evaluate for segmentation, object detection, and tracking rely on this metric, and models with high IOU values are considered as a SOTA model. However, IOU can't be directly used as the objective function to be optimized, and instead, other approximate functions or a surrogate loss are used. Why? The main reason is that there is no strong correlation between minimizing the commonly used losses such as L2 norms and improving IOU values. Let's see the figure below together. Here, the black box is a predicted bounding box and green box is a ground truth bounding box. For simplicity, let's assume that bottom left corner is fixed. If we define the loss as L2 norm, in other words, Euclidean distances between top right corners, three examples will have exactly same loss since all the top right corners of predicted bounding boxes are on a circle with a fixed radius centered on the top right corner of the ground truth bounding box. But you can see that their IOU can have a wide variety of values. This example shows that there is no strong correlation between minimizing commonly used loss and improving IOU. So, the authors introduced a generalized version of IOU, GIOU, as a new metric for comparing any two arbitrary shapes. Let's see how it is defined. We can obtain GIOU by subtracting this term from IOU. Here, C is the smallest enclosing convex object. I will elaborate this more with an example. Let's assume that we have two boxes A and B as in the slide. In this example, C will be obtained as follows so that it encloses both A and B. So this term corresponds to these areas with red color. Then why this GIOU can be used as a loss directly? I will compare GIOU with IOU. First, in non-overlapping cases, IOU value is always 0 regardless of box's distance, and IOU has 0 gradient which affects both training quality and convergence rate. In contrast, GIOU will have a negative value in non-overlapping cases and it will become smaller and converge to -1 if two boxes are very far from each other. Therefore, maximizing GIOU implies maximizing IOU when boxes are overlapped and minimizing distance between boxes when non-overlapping cases. Due to these properties, GIOU has a gradient in all possible cases and we can use it as an objective function. As an experimental result, the authors evaluated GIOU and 2D object detectors such as FASTER RCNN, Mask RCNN, and YOLO V3. More specifically, they replaced original losses in the above detectors with GIOU loss. You can see that replacing default losses to GIOU losses improved the mean average precision MAP in all detectors. As a conclusion, the authors introduced a generalization to IOU as a new metric, namely GIOU, for comparing any two arbitrary shapes. We saw that GIOU has all of the appealing properties of IOU while addressing its weakness. Therefore, GIOU can be a good alternative in all performance measures in vision tasks relying on the IOU metric. Thank you for listening.